Okay, let's begin. So, one of the first parts I talked about was expected value, right? I said the expected value is your mean is your average. I proved to you that finding the average of the given variables that you have is exactly the same as finding the x variable, which is your data, multiplied to the chances of getting that data and you sum it all together. Okay, so that's how you find the average or the mean in the long term. Okay, so the example I gave to you was if you flip a coin and the chances of getting heads and tails is 50-50, what do you expect? What is your mean? What is your long-term average if I flipped it 10 times? Okay, flip the coin 10 times. What's the average, or what do you expect to get if I ask you what's the chance of you getting tails out of those 10 flips? You'd say about 5, because you did 50% of 10. You know, I said if I flipped 100 times, and I said what's the average, or what do you expect, how many of them would you get tails? You'd say 50. Okay, and it's that same concept. That's what the expected value means. It's just the average in the long term. Okay, then you got the next part, which we then go to variance. Now, expected value, I think a lot of people understand, is the mean. You can say long term, what you sort of predict. Variance describes the data in the sense that your actual data, what is the spread, meaning how far off is it from the actual mean? What you expect? What is the error? What is the problem? How much of that problem dictates how accurate your data is? Okay, so that's how I tried to explain it to you. I said, in order to figure out your variance or how much you've gone off from your mean, is you take your data, x, minus from your mu, the symbol here just means your mean, is what you predicted. So if I predicted you get 50 and you got 60, then I'm 10 off. If I predicted that you got 40 but you got 50, I'm still 10 off. Okay? So whether it's 50 up or 10 up or 10 down, I am still in error of 10. The issue with this part of the formula where you say take your data minus your prediction or my prediction, the issue is you can have negative 10 and positive 10. If you add it together, negative 10 plus 10 will make it 0. That would imply that I have 0 error, which is not true. The truth is I made an error of 10 every time I made a prediction for you. Okay, and it's twice. So technically, the net sign error makes a problem, which is why you square it. You square it to eradicate that negative problem. So if I had 10 plus error, so if I made a prediction you get 50 but you got 60, then it's 10 error, positive. Or I made a prediction that you got 50 but you got 40, then that's still 10 error. But if you square the negative 10 error or square the 10 error, it's the same. You've got 100 and 100. What's the issue with that? Well, when you square it, now you're saying that I'm 100 off. But I'm not 100 off, I'm 10 off. Okay, so that's what the variance, it gives you a nice, if we squared it all, you get a picture. You get a variance, or the average overall, you get a picture of how bad my prediction is. That's what the variance is, the spread. But because it's not accurate, you then do the square root because you squared it. The square root gives you your standard deviation. Standard deviation is nice in terms of intervals. It tells you the space of, depending on which graph you have, it tells you how spread, how wide is my error. Is my error very narrow? So the smaller number, the better my prediction. The larger the number, the worse my prediction. It just means I've got a lot of errors in my prediction. I predict you get 3, but you get 100. That's how bad it is. It's very large. So my aim is to keep variance very small. If variance is very small, then my standard deviation is even smaller. If it's very small, then it means my prediction or expected value is more correct. Okay, so you're trying to keep it within that sort of expected value, the mean, what you expect to happen. Okay. All right, so that was the theory. Now, there is this formula right here. It says the alternative computational formula for variance is. I highly recommend that when you get into the exam and you're practicing these questions, get used to using that one. The theory is nice to use in the first one. So I'm just going to draw this one out so you can see. This is nice theoretically. This is nice to solve. So if you needed to understand what variance is and where it comes from, this is great to explain it. But if you had to use it in your exams, this is the one you'll be using most. Okay? So the question is, where does this come from? Well, everything comes from theory. That's what I've always been trying to teach you. I'm teaching concepts and theory, which is what I'm going to show you today, how variance leads you to the formula. Okay? But in order to do that, you have to also understand the properties of the expected value. And that's the aim. So I've got a couple of properties that aren't in this summary for the expected value. And then I'll show you what the variance is. Once you understand those two, we then talk about the one property about standard deviation that you use for all chapters. Okay? So let's have a look. Other properties of expected value. Sometimes we don't actually just find what we expect in, let's say, a random set of data. For example, the scores in this classroom. Your scores cannot be predicted in the sense that it follows a function. Most likely it's going to be random. You know, some of you are geniuses, it goes up. Some of you aren't, it goes down. Some of you try really hard, and you still do well, or you don't do well. So it's very random. So that's why we say it's a random data. Discrete random variables. Okay? But let's say there was something that you can predict. Take an example of the weather. If you do the weather, it goes at speed, and you can see the clouds moving in a certain direction, and the width, and the area of the clouds, and how dense it is. You can predict when it might rain, hence the weather forecast. Then, in that sense, there is a pattern. It's not random anymore. Your set of data is actually now predictable. So we now say, what if it was the expected value of a function, a model, something that you can predict? That's what a function is. A function is to use to model something so you can predict. So what if you had to find the expected value, meaning what do you expect in long-term average? What will it be? In that case, it is no longer a value or set of random variables, but it is now a function. We normally call it g of x. Could be f of x, doesn't matter. The point is, what if you found the expected value of your function? Of a function rather than a data. Okay, so the function is a pattern. That's your function. What do you expect of this function? So, has that changed things? Not much. Still the same concept. Whatever that function is, you've got an x variable, and it goes into this function, you get a number. What's the likely chances of this number occurring? Still, it's the same thing. Add your function, that value, multiply to the probability, the sum of that. It's still the same. You're still finding the average. You're just saying find the average of your function. The only difference here is you have to do something to the value before you multiply it to the data. So a quick example could be something like this. Normally, this is your set of data. Let's say the probability was, I don't know, 0.2, 0.2, 0.3. What does that give you now? That's 0.7 and 0.3. Okay, so it adds all to 100%. Then if I ask you to find the expected value from what we understand in the previous page or slide, you'd say it's your data times the chances of your data occurring plus 1 times 0.2 plus 2 times 0.3 plus 3 times 0.3. And it gives you your expected value, which is e of x. Okay? That's your expected value. Well, what happens if you then found e of a function of x? So let's say I can predict, I model this, and I say g of x is equal to 3x plus 1. The only thing that changes now is that instead of 0, you now have 0 times 3 plus 1, which makes it 1. So now you have a data where it's 1, and the probability of it occurring is still the same. You still have 20% chance of this occurring. I'm just saying I'm affecting my x values or my data. Okay, so I'm changing my data in the sense that I can predict using this number, done. If you have to think about it logically, it would be something like the person studied 10 hours. So 10 times 3 is 30, plus 1, that's what they're going to get for their exam, 30%, 31%. Okay, so it varies in the sense that 10 hours or 20 hours or 50 hours makes a difference. If we, for some reason, can predict the number of hours you study actually equates to your percentage on your exam, then there'll be a function. So how does it change things? So instead of 0, it becomes 1. Instead of 1, it now becomes 4. Instead of 2, it becomes 7. And instead of 3, it becomes 10. But your probabilities stay the same. It's just that the values of these are all now g of x. So if I asked you to find the average or the expected value of this, you still do the same. You'd say take g of x times 0.2 plus take g of x times 0.2 plus g of x times 0.3 plus 10 times g of x times whatever, and you add the probabilities together, and that gives you your average. Okay, so that's a theory. Now, if we understand that theory, I can now ask you the example for the random variable x defined in, this is example 16, which I'm just not giving you the theoretical background, but this is their table. From example 16 and this is example 17, this is their table. You started off with 0, 1, 2, 3, that's your data. Let's say, oh hey, it's 3x plus 1, 2. Must have been something that came in my mind. Anyways, there you go, 3x plus 1 as well, so same concept. You are now to find the expected value of a function. And this function is linear. This function is quadratic. You'd square it. How does it change things? Well, you get two different tables. You get either the first one, which is x now becomes 0. Wait, not 0. 0 times 3 is 0 plus 1 is 1. 1 times 3, so 1 times 3 is 3 plus 1 is 4. 2 times 3 is 6 plus 1 is 7, and 3 times 3 is 9 plus 1 is 10. Yeah? But your probabilities all stay the same. 288, 0.432, and 0.216. So that's for A. And to find the expected value, we know that you take your data times the probability, because that's finding the average. Take that 1 times this, plus 4 times this, plus 7 times this, plus 10 times that, and you get your expected value for 3x plus 1. Same thing for the second one. You would then say B would be probability. Now you're changing x values to squaring it, so 0, 1, 4, 9. Okay? And the probabilities still stay the same. And then you find your mean of this. So it's still finding the average, same thing, same skill, same theory. All I've changed is my data. Okay, that's all I'm affecting. It's sort of like transformations. The dilation changes your x values or y values, but the shape of the graph stays the same. Same thing here. Okay? So if I got out the answers for you here, so I've just typed it all out, you can actually have a look, but here's the point. Same technique, 6.4, and if you do x squared, if you follow the technique, then you get 3.96. That's how you answer these questions. Unlikely to come on the exam. What will likely to come on the exam is this part. I want you to notice things. We found that if we were to find the expected value, so I said you take 0 times, take your data, times this, plus take your data, times this, plus take your data, times this, okay? Which is what this is saying. X times the probability, and you sum it all together, is what you're going to get, 1.8. What we did before was the expected value of 3x plus 1, we get 6.4. Now the interesting thing is, if you actually think about it, or not think about it, I can actually show you why it works as well. But what they noticed is that the expected value of 3x plus 1 actually is the same thing as saying 3 times the expected value plus 1. So the expected value of a linear function, where you have 3 times the x plus 1, is exactly the same thing as you just found the expected value, times it by 3, and add 1. So, in our case, we have 1.8. So if I took 1.8, and I times it by 3, and I add 1, magically it becomes 6.4. But if you think about it logically, it makes sense. Let me show you. If we said, this is the theory, let's compare it to this.
I've got a linear equation where it is 3x plus 1 multiplied to the probability of x. Think about this is just distributive law. If I multiplied the probability to 3x, I'm going to get 3 times x times probability of x. And hey, look at that. X times probability of x. What does that remind you of? This one. That's your expected value. Which makes sense why you have 3 e of x. The question is, well then, why isn't 1 times p of x just plus p of x? Why isn't this part here just p of x? And the logic to it, because you're summing, remember this is the sum. If you took the probability, let's say, I'm going to change the numbers, let's say 0.2, 0.2, 0.3, 0.3. Okay, instead of those random numbers there. Logically, what you're doing is you're saying, if it was 0.2 times 1, you've got 1/5 of 1. And then you say, take the next probability times 1, let's say another 1/5, plus another 3/10, plus another 3/10. Well, logically, you get 1 whole of that constant, which makes sense why, whatever that constant is, you're just going to get 1 whole of it. If you times the probabilities and you add them all together, of course you get 1 whole, because the probabilities all add up to 1. So effectively, you're just saying probability of 1 total is 100% times constant. That's why this leads on to this one property that I'm saying is going to be an exam that isn't in your, sorry, to be here. Oh, I made a mistake there. That's your rule. Now this rule is not in your summary, and it's in a few years before it was not in your exam formula sheet as well. But they use it to test how well you understood that. The expected value of a linear function is equivalent to saying the dilation factor times the expected value, and that last constant there, remember probability of the total probability is 100% of B gives you B. This is the property. Now you can either memorize this, which I think most students do, or understand what I was just teaching you, and you always remember this property. I wrote up here, it says an exception is when it's a linear function. Reason being is because x hasn't changed, which is the data. As soon as x changes, when you have x squared, x cubed, it's no longer a dilation factor, it's just the same x value. So this only works for linear. And you can prove that in the last few slides that I had. Just going back, right here. I told you to find e of x before, e of x squared. If according to what I'm saying is true, if you can take the expected value of the function, or you take the function and sub the expected value in, okay, so what I'm trying to say is this. Instead of saying e of g of x, we're saying that this is not the same. But it happens to be the same for linear. Because for linear, e of ax plus b, if you sub e of x into the x part, you actually get a times e of x plus b, and that happens to be true. Now that only works for linear. Whereas if we tried it over here, if it's expected value of x squared, and I subbed in e of x into x squared, so if that's x squared and I sub that in as e of x, then you find that e of x squared doesn't actually equal the same, because e of x was 1.8, that's what we found. If you squared it, it gets you 3.24. In the previous slide, I showed you that e of x squared actually gives you 3.96. Therefore, this is not true. Okay? And so what I'm trying to say there is that in this property, this only works for linear. Okay, that's what I'm trying to show you in that slide. So if you were looking at this video again, or you're looking at the slides, it doesn't work, the functions do not work for anything else but linear. Okay? Alright. Actually, I'll just go back and I'll just re-emphasize this point. That's what I'm trying to say here. Okay? I'm trying to say that the expected value of the function does not equal if you sub the function back in. It only works for linear, is what I'm trying to say. All right, so that's one property. Now, the nice thing is once now you know this one property, there's a couple other ones that are interesting now. You can also use the same theory and prove it, but the expected value of two different variables, or the sum of two variables, is exactly the same as the expected value of each one individually. Okay? Now, let's move on to variance. Now that you know those 2 points, those two properties, let's have a look at variance. I told you that this is the computational formula. Yes, you can memorize that. Or every now and then you can ask me and I'll tell you what the answer is or what the formula is. Let's think about it. Let's say you didn't have me and you have to figure it out in the exam yourself. This is the theory. What was my theory? Take your x value or your data, subtract the prediction. Square it to avoid the negatives. That is your variance. So, if I look at it, if that's my theory, let's see what happens if I actually square it. This is quadratic. Square A, square B, times 2 to every term. So you've got 2 times mu times x, I get this. Square the first one, I get this. Square the last one, I get that. Now, if we had to look at this, using this property up here, if we're using this property up here, I can split this up into x as my group, plus this entire thing as my y. See that? I'm using this property here where I can split it up into two expected values. So what I'm doing here is I've got expected value of x squared. Instead of plus, it can be minus. Add or subtract, same thing, and I've now got the second part. So I'm adding on to negative 2 mu x plus mu squared. Nice thing is, mu is actually your expected value, okay? That's your expected value. And the nice thing is, we know from the previous property, where I gave you e of ax plus b is the same thing as a times the expected value plus your constant. This is your a, that's your x, this is your b. Therefore, you get 2, negative 2 mu, which is a, times the expected value, that's what I'm doing here, plus your b. That's all I did there. So I used the two properties I just showed you to get those points. And therefore, we now can summarize it all together and we can say that means negative expected value is just mu. Mu times mu is mu squared. Conveniently, you got negative 2 mu squared plus mu squared. Well, you get minus mu squared. And mu is just your expected value, which happens to be that. Okay, so computationally, this is nice. Why is this nice? Because we can find this easily. Why isn't this nice? Because you have to find the expected value, then take your data, minus each one, square each one, and then find the average of that. It takes too long. This one is more efficient. So if you're doing your exams, your SACs or exercises, please get used to this formula. It's nice to know the theory from here. Use this to solve. Okay? So this is the one key one I want you to learn. Make sure to use this when you're in exams or SACs. Okay? They're much easier to do. All right. Let's have a look. Now, this property here, in case I'm going to overthrow you with so much proof and whatnot, you can take that as a fact if you want. Okay? Variance of a linear equation now, so a linear function, is equivalent to a squared, which is the coefficient, times your variance. If you're interested in the proof or the logic to it, again, it all goes back to theory. Understand the theory and you can prove this. And I have done it over here for you, okay? And I hope the brackets and all the A's don't scare you, but if you take your time to think about it, it all makes sense. Okay, so I touch it out again, go in the same theory. Variance of a linear is the same thing as the expected value of the linear data, so that's your data minus what you expected, and then square it. Okay, that's what I did here. The nice thing is though,
mu squared of mu is exactly the same thing as saying expected value of ax plus b, which is the property that you knew before. The nice thing about this is you can write that, no way it gets a bit scary, is a of expected value plus b. And then, the nice thing is the two b's cancel out here. You got b minus b, because of the negative on the outside. And you can then take a factor of a out. You factorize a. This is x, which is your data, minus your expected value, which, voila, is the same thing as your theory here. X minus expected value. And it's all squared. So if I square each one, you then get a squared, and then this is really just your variance. And the nice thing is, the question is, why can you take out a squared outside the expected value? Because you think about it, remember the average means add all numbers divided by the probability of the number of numbers. If I times it all by 2, well, you can take out 2 as a common factor from every term. So of course it goes out to the outside. So that's what that is, and that obviously gives you a squared variance x. But you don't have to know that. I'm just showing you the logic to prove my point. Everything you need to know, whoops, goes back to theory. Okay? Theory is where all the formulas come from. So if you understand the theory, you don't have to memorize the formulas. They'll come out from the theory. Okay? Alright. That's variance. I know it's hefty. I just went through expected value. I just went to variance. And I explained what expected value is, and I explained what variance is. It's the spread of the data. And then we finally, this is just an example so you can go through to practice the formulas if you want. Okay? But we finally get to standard deviation. Standard deviation is just a better measure of the spread of the data. And one last property that I'm going to end off here. Okay, I know it takes a while, and I want you to practice that last exercise. That is your key, okay, for your exams. Everything before that was revision. This is the only part that's year 12. Okay? This is the last property. If this scares you, don't. It's just the symbols. Let's read the symbols. You got probability of random variable x where it is between mu, which is what you expected, minus 2 times, this is called sigma, but that sigma is your standard deviation. And the upper boundary is called your expected value, or your mean, plus 2 times the standard deviation equals the 0.95. What does that mean? Very simple. It just means 0.95 is 95%. So 95% of your data, which is your x, 95% of your data will fall in between 2 standard deviations, which is your spread. Okay, your spread, how wide is your data? 95% of it will fall under 2 standard deviations. If I had to give you a visual image, let's say the mean for our class was, I don't know, 68%. Okay? If that's the mean, then where would 95% of my students in this class fall between? Let's say this is mu, which is 68% minus 68% minus 2 standard deviations. So if I can use all the data, find the variance, square root the variance, gives me a standard deviation, which is the spread. 2 of these intervals, or 2 of these spreads in the interval, if I minus 2 times the standard deviation will give me the lower boundary, whatever that percentage is, to 68% plus 2 standard deviations, which is the spread on the upper half. So you've got spread upper half, you've got spread lower half. This should generally, we're not saying it's always, we're saying generally or usually, this is equivalent to 95% of the data. Okay? And that's the first step. That's one property that you need to know for standard deviation to answer questions. Okay? So please write that down in case that symbol scares you. It isn't. If it ever asks a 95% confidence interval, that's what that is. I'm going to write that down in case you guys are going to accuse me of not telling you this. This is another way of explaining this in a question.
is they normally say 95% confidence interval. So if you see that question, because last year I had a couple of students look at that question and said, "You never taught me, sir." I said, "I totally did. I did examples on it as well. I just called it differently. I just said it's 95% of data." And they didn't know what 95% of confidence interval is, so that's all it means. Confidence interval, what does that mean? You're confident that between these 2 points, 95% of your data fits there. Same thing, yeah? It's just I didn't say it in those words, so I'm saying it now. 95% of your data, you're generally pretty happy or know that it fits between 2 standard deviations below or above the mean. That's what we call, by name, 95% confidence interval. Okay? Same thing. Is that a question? Sorry, I can't hear you. Don't worry. Okay, I'll come back up soon. Right. But that's about it, and this is just an example of how the question would have been posed to answer that question. But I want you to practice that exercise. Take in what I was saying, it's all theoretical today. Practice that exercise, but try to absorb what it means, because it will carry on through the next 2-3 chapters. Okay, those are the concepts, and it will stay the same throughout. That's why probability is easy. Okay, because you just have to understand that one exercise, and it carries on. Theoretical clue gives you the formulas. And I'll show you the formulas for the other chapters, but it comes from this theory. Okay? Alright, we'll call that a day, and I'll leave that up. This is the confidence interval problem. Go back and do the expected value variance and standard deviation, and when you're happy with those, look at standard deviation. Okay? Alright, I'm going to pause the video, and then I'll put you back into this.